So good afternoon, everybody. I'm just formally start here the class, and a student just asked here a question about the crude birth rate and the crude death rates. Let me just go back there so everybody can follow. That was in the introduction, right? Which chapter?
That was, they talked about it a little bit as well, but I'm
Yeah, I don't. No. Yeah, you can ask the question now. I mean, you were just asking about the how it's calculated.
Yeah. So, like, it is division 10. So I know it's, I'm just trying to figure out where that
You usually divide the number of births by the total number of the population, then you multiply by 1,000. That's how it usually is. Let me just get the slide specifically here about right here. So this is the slide from the introduction, slide 73. And the crude birth rate, you get the number of births divided by the population. But if you get the number of births for a specific population, a specific year, and divide by the total size of the population, that number is going to be really small in decimal places. So in order just to have it an easier way to interpret it or to understand, you multiply it by 1,000. And the same thing applies for the crude death rate. You get the number of deaths divided by the total population and 1,000. So how do you interpret this result? For example, here for the US, back with data in 1950, 1955, you had 24 births for every 1,000 population. So on average, if you got 1,000 people in the US back in 1950 and 1955, they would produce 24 babies in that specific time period. And that dropped to below a little bit of 12. Let me see, getting more recent data here, more current data. A little above 12 now when we are. So this is saying that out of 1,000 people in the US, we are producing around 12 babies in this specific time of 2015 to 2020. So that's how you interpret that. Usually for us, it's easier to interpret these rates when they're in percentage term. For example, in the last class, I showed you the dependency ratio. We get let's say the youth dependency ratio. You get the number of children divided by the people in working ages, multiplied by 100. So you are just saying, you're comparing what's the percentage of children in comparison to the percentage of people in working ages. And percentage is usually easier to understand. So if that rate was 90, what does it mean? That for 100 people in working ages, we have 90 children, right? In this case here, we are saying that for 1,000 people, this is the amount of babies being born in the US in that specific time point. Is that clear? Oh, you mean the natural increase, right? The natural increase, you get one minus the other, and then you divide by 10, because then you go back to 100, right? Because here you multiplied by 1,000. And if that's not the correct term for that, when you get the crude birth rate minus the crude death rate, that's the natural increase, right? The natural increase is given usually in percentage terms. But if you got this crude birth rate here and the crude death rate by 1,000, after you subtract one by the other, then you divide by 10. Because divided by 10 is the same thing as you're dividing this 1,000 by 10, then you get 100. So the natural increase is usually reported in percentage, right? Or if you had the number of births, total population, number of deaths, and total total population and you didn't multiply by 100, by 1,000, you just subtract one by the other and then multiply by 100. So it just depends on how the crude birth rate and the crude death rate that you are analyzing is calculated. So for example here, let's get for the first year, the first time period, 24 per 1,000 crude birth rate. And here, let's just make it easy. Let's say 10 per 1,000 crude death rate. So 24 minus 10 is 14. And then you divide by 10, 1.4. 1.4% is a natural increase. Okay, so that's the idea. Cool, sure. No, yeah, feel free to ask this kind of questions because the whole course is really connected in terms of the chapters. So I will be talking about one chapter at the middle or at the end of the semester, and it's completely related to what we have talked in our first day of class, right? But yeah, so the idea is that this number here will be so small that it multiplies by 1,000. But then when you want to do natural increase, you convert it to 100%. And for do that, you just subtract crude birth rate minus crude death rate, and then divide by 10. Cool. And you guys at home, I cannot see the chat. So please, if you want to ask any question, just unmute yourself and ask the question. Cool. So I will continue or start the chapter about world population change over time. I mentioned the last class that a lot of the slides here are extra material, so we're not going to cover them in detail. And here we're going to talk about these 5 major topics in demographic change that the world has been experiencing in these last decades, in these last centuries, which is related to an increased population size, improvement in mortality, so people living longer, fertility declining a lot. It's still a lot of countries with more boys being born than girls in really much higher numbers than expected. And also, because people are living longer and having fewer children, we have a higher percentage of the population in older ages, right? And I will show you here a series of graphs about increase in population size in the world in these last centuries and thousands of years and decades from different sources, but they're all talking about the same thing, just a different ways to show the same results, okay? So here we are talking about more than 1 million years ago and circa like the 2000 year. And just showing you that in 13 years, we will add the next 1 billion people in the population. So this is data from 2011. So that's data from the United Nations Population Division, the UNPD, from 2011. And they were projecting in 2011 that by 2024, we would reach 8 billion people, from 7 to 8 billion people. So we would increase 1 billion people in only 13 years. And this is just interesting to see how steep this line has been in these last decades, in these last years, because the population size was kind of small, was increasing, but was still small and increasing at a much slower pace than we start to see starting on the 1800s. And the 1800s is exactly when we have the Industrial Revolution, and we have improvements in health services, and we have improvements in technology, in medicine. So people start to have more access to medications, to vaccines and everything. And also we have a huge drop on infant mortality rate. And then population started to increase really fast. So here, it took like all these years here, all these thousands of years here, to reach a population of 1 billion in 1800. And then it took only 130 years to add another billion. 30 years to another one, 14 years, 13 years, 12, and then 13. Right? So just to show you how we added another billion in a much faster place in these more recent decades than what we saw previously. And just doing a zoom in on this graph, just looking here from 1950 and doing projections up to 2050, that's the second graph here. So it's just doing a zoom in on this area of the graph. We have this one here. And in this one, we kind of also have the additional information. We are not just looking at the overall size of the population in the world, but looking at the population of the more developed countries. That has been, it increased in previous decades, but then now it's expected to get stable to these next decades up to 2050. Other less developed countries increased, but also expected to kind of like stabilize in these next years. But then what we see in Africa, in China, in India, in Africa, one continent by itself, and China and India countries by itself, their share of the overall population increased a lot in these last years and is still expected to increase for these next decades. Not much, China is not changing so much from here to 2050. India is still increasing. If we look at this width of this graph here and up to 2050, but Africa, the whole continent, is really expected to increase a lot, right? So what we're going to see in these next decades is not that much an overall increase in the size of the population in the world, but we're going to see an increase in the size of population in specific areas. So we're going to have a higher percentage of the population living in African countries and in Asian countries compared to other parts of the world, okay? And I'm going to show you a table that shows that indicates that really clear. And we have also seen a lot of improvements in mortality. When we say that we have improvements in mortality, it's not that mortality is increasing, it's exactly the opposite, that people live longer. So the mortality rates are declining. And when the mortality rates decline, we have an increase in life expectancy. Life expectancy being the average number of years that people live on average, considering the mortality levels of that population at that time. And these gains were observed in this past 2 centuries, especially since the end of World War II. After World War II, a lot of improvements in health, in technology, in medications, and that improved the overall health of the population and decline and helped mortality to decline. So that has been the most important thing in human history. It's a consequence and cause of new way of viewing the world. So we see the world in a more rational way. Now we think that we can change, we can act with all this knowledge that we have from science and everything, the way that we behave, what we eat, how we exercise and work out, and all that knowledge about habits that it can improve and affect our life in the future is taken into, it changes our daily activities. So we think much more as rational people, thinking that our actions are not driven by some special force beyond us, but by our own actions, right? So it's a more rationalized world. And transitions that accompanied these changes have been enormously transformative, because exactly all these changes, all these improvements in how we live our daily life affects the way that we have fewer chances to die, we live longer, and we also decide on how many children we're going to have. Like the couple decides how many children. And in the past, when there was like no concern about health of women, the number of children, they didn't realize that affects women as well and affects their health. So by having fewer children, it positively affects the health of women. And overall, the household is going to have to spend fewer resources to raise children as well. So all these different factors are interconnected and have been really important on how our society have been developed in these last centuries. And here's an example for 3 developed countries, Japan in dark red and like a little pink here, for male and female life expectancy in Japan, the US, dark gray and light gray for male and female life expectancy, and then Denmark, male and female life expectancy, let's say brown, orange here, and yellow for women. And this is how life expectancy has been increasing over time. This is data from a little before 1935 up to 2010. This should show you how it increased so much in Japan, that nowadays has the highest life expectancy. You still see differentials in terms of life expectancy by sex. You see that women living longer than men, and it increased a lot exactly after World War II, right? So now here women living above 85 years of age, and this data here is the average number of years that people are living in Japan, or that women are living in Japan, considering data from 2010. And that's, of course, some people live longer than that, and some people don't live as long as 85 years of age, but that number is really big compared to other countries in the world. But even in the US and in Denmark, you also saw these increases in life expectancy, and that happens all over the world. But still you see these differentials by sex is still happening, is still existing, even in more developed societies, and always, on average, women living longer than men, okay? The third point, fertility has been declining a lot, and I mentioned in the last class, when the couple is producing fewer children that they would replace themselves, and if we take the average of across all the society in a specific year, we say that fertility is below the replacement level. So you'd think, oh yeah, a couple would have to produce on average 2 children, so would replace themselves in future generations. But usually we think about replacement level as being 2.1 children per woman, because we have to consider that some of these children will die and will not reach reproductive ages, especially women. And it's still because we have more boys being born than girls, so we give a little more to this total fertility rate, to this indicator, in order to have enough women reaching productive ages between 15 and 49 years of age so they can replace the generation of their parents. And fertility here, we are getting information only for women. So when we talk about total fertility rate equals to 2 or equals to 2.1 to be more specifically, we are talking about how many children on average women are having. And then we expect them to have more than 2.1 on average because we replace them and their partners. And here we have the total this is actually the population growth rate between 1950 and 2010. It increased up to the end of the 60s and beginning of the 70s, and it started to decline again. So the period of most rapid population growth is behind us. Since its peak, the growth rate has declined falling roughly by half in 40 years as women have had fewer children. So it was around 2% growth rate, and now we are almost at 1%, right? So in the point here of this analysis is that this population growth rate decline, overall size of the population now, it's still increasing because it's positive, it's above zero, but it's not as fast as it was in the 70s. And it's related to fertility. And then when we look at the total fertility rate, and here divided by 3 groups, we have the world as a whole in the middle, the orange line, the less developed countries, excluding China, in the red line, and excluding China just because China would bias this information because the population is so big, and also because they had another dynamic because of the one-child policy and fertility declining so much in these last decades. And in yellow, we have more developed countries. But even when we exclude China here, we see that less developed countries also experienced a huge decline in fertility. On average, from 6 children per woman back in 1955 to around 3 children per woman somewhere between 2005 and 2010, right? So the global fertility rate has dropped from 5 to 2.5 in roughly 50 years. And the average woman in developing countries now, they have 3 children. That's what I said before, compared to what they had 6 children 5 decades ago. And more developed countries as well, they even dropped way below the replacement level, and you see some increases in more recent years. And just by looking at this yellow line here for more developed countries, there are several studies being done by demographers trying to understand the reasons that women are having fewer children and below the replacement level, below 2.1 children per woman. And people are concerned because if fertility declines so much, we are not going to have in future generations, babies or people, to replace the generations of their parents. And that might cause a too strong population aging that would create a lot of pressure on the government, on public spending, and so on. And one discussion that has been done, and I will discuss that more in detail in the fertility chapter, is that a lot of these countries, what happened is that women start to invest more in their education and then getting a job before forming a family and having children. So they postpone the age in which they would have children. So there is a postponement in fertility. But after they finish school, after they finish college or whatever level of education they wanted and get a job and then form a family, they tend to, after that, start having children to the desired numbers that they had, which is kind of similar to the previous generations, around 2 children per couple, right? But because they postpone their fertility into later ages, then they're going to have fewer years to reproduce. So maybe they want to reproduce more, but they won't have enough time because of biological reasons. So this postponement in fertility, if women can catch up, then we might see in more recent years this fertility going up a little bit more and going closer back to 2.1 children per woman. But if it doesn't catch up, or if women still, they think, oh, 1 child is enough, we don't want to have 2 children, then fertility will continue under replacement level. Korea, for example, has really low levels of fertility. Most of the couples there, they decide to have just 1 child and that's it, because it's so expensive to take them to school. It's so expensive to provide them a good life. And the same low levels of fertility we see in some European countries as well, like Italy, Spain, and some Eastern European countries as well, because there is not much child support. There is not much support for working mothers who have children, so they just don't have as many children, right? And that might cause fertility to keep staying lower in those countries. And the challenge for policymakers is to know which kind of policy we can implement to kind of make people have more children, like maternity leave, and actually also paternity leave as well, to make people want to have more children. So there's a huge discussion about that. And like I'm saying, just looking at specific countries within these more developed countries. What I wanted to emphasize is that these graphs, these general graphs for groups of countries, a lot of demographers try to look inside them into the stories and the history of each one of these countries. Okay? We still have a lot of countries in the world that have a preference for boys instead of daughters. And what's usually the natural or the biological sex ratio at birth? It's usually around 105 boys per 100 girls. But you see that some countries like India, South Korea, China, or this area in Northwest India, they have sex ratios at birth much above 105. Because fertility in those places is low, it's getting lower, and there is still a cultural preference for sons, and these preferences are not going to change anytime soon. And the reasons are a little different as well. You know, like in India, there is still a lot of poverty going on there, and these preferences for sons is more related to exactly families trying to improve their wealth. In China, it's also related to the one-child policy and also to economic development that made fertility decline so much. So people say, okay, you want to have children, so let's try to have boys first. And in South Korea, although it's a more wealthy country compared to India and China, it is expensive to have children. People are tending to have just one child, and again, because of cultural aspects, they have this preference for boys. And then you create this really unbalanced sex ratios at birth, much above 105 boys being born for 100 girls. Okay? And going a little bit, some observation about China specifically, the biological normal level of sex ratio at birth is around 105 males for every 100 females, like I mentioned before. And several societies do have much higher sex ratios at birth. And because they have been experiencing a really rapid decline in fertility, a really rapid fertility transition. And in the context of really rapid fertility transition, a fertility decline in which those countries culturally have a preference for sons. And then the availability of ultrasound to determine sex, people have an easy access to abortions, and that affects sex ratio at birth. Why is that important? Because then later in life, at working ages, these babies, when they grow up, you're going to have many more men than women, and then you start to have some difficulties of finding partners and forming a family. And more recently, I just saw this news article in the New York Times just showing how the daily life is affected by that. Like in parks in China, men of working age would put signs advertising themselves why they would be good husbands. Oh, I'm wealthy, I have a car, I have an apartment, I have this and that, I have a good education. These are my earnings. So pretty much it creates this marriage market of men trying to find women because there are not as many Chinese women available because they were not born, right? And then you also see stories of Chinese men going to other countries around China, North Korea, South Korea, trying to marry women and then go back to China. So that creates a whole new dynamic. And then you start to have a lot of men that don't get married, and those men that are not get married, previously they already had lower levels of education, lower levels of earnings, lower levels of skills, so they will tend to stay in poverty, and that will increase poverty for that specific group of people in China. And then later in life, when they get older, they won't have any access to any benefits, and that will affect their health as well, okay? So just this fact of having an unbalanced sex ratio at birth in specific countries has effects on the future decades of how that country is going to have to deal with the composition of the population by age, right? And by sex. And this is a graph about the total fertility rates in China from around like from 1950 to 2010. And then you see that, I mean, the one-child policy started being implemented in 1979. And what was happening before that? Fertility was already declining. So this graph here kind of shows, okay, the one-child policy might have had an important effect on the decline in fertility in the country, but it was declining before the implementation of the one-child policy. Exactly because you start to have economic development, people moving to urban areas, being more expensive to raise children, and then fertility starts to decline, as any other country that passed through industrial revolution or improvements in the society. And although we call it one-child policy, or it was formally called one-child policy, and in 2015, you see that the total fertility rate, it was, even in 2010, did not reach the level of 1. It was still above 1. Exactly because some women were allowed to have more than one child, and even some had more than one child, but they would not have access to education or to the public system as the other woman who had one child would have. But some women got exemptions, but overall, only the fact that you had this policy that was forced from the government on the people without any consent or anything, it has an effect on the minds of people, and it increases the imbalance of the number of boys and girls being born in the country. Cool? Any questions? So the destiny of China is already set. It's discussed in the textbook. Why does China have a high sex ratio at birth? Exactly what I mentioned before, prenatal sex identification via ultrasound, followed by abortion if women were pregnant of a daughter. What will be the result of the high sex ratios at birth? Between 1983 and 2010, over 41 million extra boys were born than girls. There's a larger number of bachelors in China than the total population of California and the total population in Texas. So it's just to give you an idea of 41 million extra boys than girls. It's a lot of people. The total population of California in 2010 was 37 million. In Texas, 25 million. So you have all this extra population that if they wanted, they will not have partners to form families in their country. And then in the textbook, there is some speculation of what could be the effects of this really unbalanced sex ratio at birth in China for the next decades. Most men unable to find sex partners will be poor, uneducated, unemployed, and migrate from rural to urban areas. So I mentioned that before. They tend to be poor, lower levels of education, and most of them won't have jobs. And more than that, they might migrate from rural to urban areas. Why is that bad? in China, there is a system in which people have to get permission from the government to move from a rural area to an urban area. If someone moves from a rural area to an urban area without the government permission, that person will not be allowed to get a job in the formal economic sector. So they will tend to get more lower paying jobs. And if that person brings their family, the children will not be able to get to access public school in the urban area if they didn't get the approval from the government. And the family will also not be able to get public health in the area of destination, the urban area. So what has been happening a lot in China, exactly because these people are maybe not married, they move to urban areas without government approval, still their lives are going to be better than if they stay in rural areas because the conditions are better in the urban areas. They still, on average, they will be the lowest paying people in the worst conditions in the urban areas. And then some people that are actually married and have families and want to get a better life, they move from rural to urban areas without government approval, but they move by themselves and their family members stay back in the rural areas because then they can access education and health public systems. But then their husband migrates to urban areas. So all that, in this case here, these regulations about internal migration in China also affect the wealth of these people. And these people are already in a bad situation because they were not able to form a family, and forming a family, you get more stable life, you tend to have a better job, and so on, and they won't have that. And then in the book, there is some debate about what that could cause in the near future. Exactly because of them being poor, uneducated, and unemployment might be associated with increase in crime and violence, increase in prostitution, increase on sexually transmitted diseases, mainly among unmarried men, and an unprecedented spread of HIV. So you have sex ratio at birth, unbalanced sex ratio at birth, more boys being born than girls, that it will affect a lot of factors in your society, crime, violence, and also health, mortality, right? And going specifically on HIV, in sub-Saharan Africa in 2013, there were around 25 million adults infected with HIV. This is almost 71% of adult infections of all the world. So 71% were in sub-Saharan Africa. In 2010, around 1.2 million people died from AIDS and 1.9 million people became infected with HIV. This data here is kind of the stock, the overall number of people infected with HIV. 70% of them, more than 70% of them, were living in sub-Saharan Africa. And this infection here happened in years from 2013 to years before. And this number here is it's an yearly number. The number of people that died from AIDS and became infected with HIV in the specific year of 2010. And the whole discussion that I started in the previous slide is that China could exceed these numbers by now, 2020 to 2030, right? So we're in the middle of this. The country is beginning to take seriously the issue of HIV/AIDS and a possible epidemic. And then now with also the coronavirus pandemic, all that mix up. So these issues here were thought before the current pandemic and was already an issue. But then the discussion is that this easy indicator of sex ratio at birth, number of boys being born in a specific country in a specific year, divided by the number of girls, multiplied by 100, can if we analyze it historically, can have some effects in the next decades of a specific country. Okay? And the fifth point is that population is getting older. Fewer children, people living longer, then you start to have proportionally more people in older ages. These graphs here are in millions, so this is not in percentage terms. This is for developing countries and developed countries. As I mentioned before, in that graph about the increase of the population over time, when I showed India, China, and Africa and other countries, developing countries have a bigger population now, and more than that, they have a younger population. Still, the number of people in younger ages, in this case here up to 24 years of age, is much higher than in older age groups. And in more developed countries, you have the opposite. Younger people being overall in fewer numbers than people in working ages. And here just some percentage to summarize it. 43% of the population sub-Saharan Africa was below 15 years of age, while 16% in Europe were children below 15 years of age. So 43 and 16, much younger population in sub-Saharan Africa than in Europe. And what about the older people? Sub-Saharan Africa, only 3% of the population with at least 65 years of age. And in Europe, around 16%, right? In data from 2010, all these things are changing continuously, but the overall pattern is that the developed countries, they have an older population, and developing countries have a younger population, but developing countries also experiencing fertility decline, as we saw in previous graphs. This age-sex structure here is also changing over time, having fewer people, or even in percentage terms, in younger ages. And this is another way to show population getting older in the world, in more developed regions and less developed regions. And this is the percentage of population with at least 60 years of age. So overall, we have higher percentage of people with at least 60 years of age in the world, from 8.1% in 1950 to almost 22% in 2050. In more developed regions, this percentage is even higher, exactly because in those countries, fertility declined before and mortality improved before. So you have more people in older ages. But even in less developed regions, you also have an increase of older populations from 6.4 in 1950 to 20.2% in 2050, as expected by the projections. Okay? And now I'm going to talk a little bit about this demographic transition, which is the major theoretical framework that we use to analyze the decline in mortality, the decline in fertility over time in the world. And what are the major consequences of that? More in-depth discussion about the demographic transition we will have when we go back to chapter 2, theories of demography. So in that chapter about theories of demography, we're going to go more in depth about the demographic transition. And we're going to also talk about specific theories, specific groups of explanation about changes in fertility, mortality, and migration. Here we are talking about the big picture. What are the major factors influencing change in mortality and fertility over time in the world? This is the graph that's showing the textbook. Whenever I have questions in the quiz, it's going to about the demographic transition and the stages in demographic transition is going to be based on this graph here. The next graph divides in 5 stages. I just like it. I will tell you why. But whenever we have questions, should don't be confusing. I will just base on the graph that's shown in the textbook. And it's also here in this slide. So in this graph, we have pretty much 4 stages in terms of the pattern and level of birth and death rates. Stage 1 had really high levels of birth and death rates, in specific times higher birth rates than death, and other times more people dying than being born. But overall, really, really high levels of birth and death rates. What it means, people having a lot of children and people dying earlier at younger ages, right? Really low levels of life expectancy. So this stage 1 is called pre-transitional or pre-industrialization stage. Right? So before the Industrial Revolution, you had really poor health, really high levels of mortality, and people having a lot of children at really high levels. What happens there? When you have really high levels of people having like high levels of fertility and high levels of mortality, the population doesn't grow as much. When you just see the difference between the birth and death rates, it's exactly the natural increase that, I forgot your name, you in the red sweater, what's your name? Erin was asking at the beginning of the class about the natural increase. Here, the area in this curve, it's exactly the birth rates minus the death rates. And exactly because people were having a lot of children, but they were dying, people were dying at really younger ages, population was not growing as much. When you start with modernization and you start with this transitional society in which you have industrialization, so now we produce food, we produce resources in a much faster manner, we start to have better public infrastructure, basic health habits, that has an immediate or a really fast influence on mortality. So people start to live longer with basic changes in health and how people live in their lives. The water system is treated, sewer systems start to be implemented, people start to wash their hands before eating. When there is a birth, everything is doing more in a hygienic environment. So you start to have a huge decline in mortality. But it's still people, because of generations of how it was, people were still having a lot of children. Women were having still on average around 6, 8 children. But now their children are living longer. They are living longer. Mortality is declining. And in this stage 2, there is a huge population growth. That's related to those graphs that we saw at the beginning of the class today, the increase in population after the 1800s, right? Exactly because mortality declines a lot related to the Industrial Revolution, and fertility, culturally, we had a lot of children, we keep having them, and then population increases so much. But then when people start to realize, hey, it's expensive to have so many children because they will survive to older ages. If we have just few children, they will survive until being adults and forming a family. So we don't have to have as many children. So fertility starts to decline as well. So declining fertility is also driven by declines in mortality, simply because people realize that they don't have to have so many children in order for some of them to survive to older ages. Of course, it's also related to changes in society, urbanization. It's more expensive to have children. But what this graph is trying to show us is that fertility starts to drop after a drop in mortality. And mortality dropped a lot, continues to drop a little bit, but begins to be more stable. But then you have this stage 3 in which fertility starts to decline, and then the natural increase, the difference between birth and death rates starts to decline. So population growth is positive, still increasing because birth rates are higher, but it's not so fast as it was on stage 2. And then you have some more developed countries in which you reach so low levels of fertility, below the replacement level, that you start to have fewer births than deaths, and you might have some negative population growth, right? So this stage 4 called the incipient decline. And this graph here that I got from this website, Our World in Data, this is the same website that I got data about the coronavirus pandemic at the beginning of our course, one of the websites that I got data about the pandemic. What I like about it is because it adds the trend of population size. On stage 1, you had high birth rates and death rates, so population growth was not actually so strong, so the size of the population was kind of stable. When mortality starts to decline a lot and fertility continues to be high, then population starts to increase really fast. So high birth rate, mortality drops a lot, very rapid increase in population size, in natural increase, birth minus death. And then in this graph here, they subdivide the stage 3 from the previous graph into these stages 3 and 4, which is pretty much fertility declining afterwards, after people realize that they don't have to have so many children because mortality declined a lot. And then we still have population growth, but not so fast as it was before. You see the orange line here, not so steep as it was on stage 2. So natural increase slows down. It's not so rapid as it was. And then it starts to even get more stable or a slow increase even when fertility keeps declining even more. And then you reach in a stage in which some more developed countries are, like Western Europe, like Japan, South Korea, in which you start to have fewer people being born, birth rate is lower than the death rate, and you have a negative population growth. In other words, you start to have a decline in population size. Okay? So this is the overall framework that we use to try to understand demographic transition in the world. Demographic transition, in this case, you're focusing on declines in mortality, followed by declines in fertility, and how that affects the size of the population. And what about migration? Yeah, migration doesn't come specifically in this graph here, but we're going to see in chapter 2 a discussion about several theories that try to explain the reasons of why people move within countries and between countries. Okay? This is a more technical information that's also in the textbook. When we are trying to understand the space in which societies are increasing, we could ask ourselves, if this country is increasing with this specific growth rate really fast, how many years would it take for the population of this country to double in size? And that's what this formula here tries to take us into. So whenever a demographer talks to you about doubling time, the demographer is trying to tell you how many years would it take for that country to double the size in population if that specific growth rate continue to be the same in these next decades. So this time it would take for a population to double at a given growth rate if the exponential model were exactly true. And this is called the rule of 69.3. This last result here is good for you guys to know, but here I don't expect you to memorize this formula or anything, but we would go more in depth on these methods on the demographic methods class, which is SOCI 320. And it's actually being offered now, this semester, spring 2021. But that demographic methods class is going to be offered only every 2 years, right? So next time we expect it to be in spring 2023. But here in Population and Society, which is offered every semester, I try to give a quick idea of these major methods that we use in demographic methods. So how do we usually calculate the population in the next years based on the population that we have from previous years? So the K0 here is the population at year 0. And the population in year T is calculated by multiplying the population at the beginning of the period by the exponential of the growth rate times the number of years between 0 and T. So let's say that we have the population in 2000, and I want to know what's going to be the population in 2030. I have the population in 2000, and I want to know what's going to be the population in 2030. That's a projection of the population, as we have been seeing already, based on UN data from the United Nations. The population in 2000, I know. I can just go back to the United Nations or some other source and look at the population of the world in 2000. Between 2000 and 2030, which is the year that I'm trying to understand, we have 30 years. The problem is the growth rate. What's going to be the growth rate between 2000 and 2030? I don't know exactly because we are just in 2021. So what demographers try to do is make some scenarios. Let's say that the growth rate was around 0.7% in these next years, or was 1.2% in these last years. And if we expect that growth rate to continue to be the same until 2030, then we can do a projection of the population. So projections of the population, if you're talking the population of the world, depends only on the growth rate here. And the growth rate, if you're talking about the population of the world, depends only on fertility and mortality. So the assumptions, the scenarios have to be driven based on fertility and mortality. What do we think is going to be in this next decades? If we are trying to project the population for a specific country, then the growth rate is affected not only by fertility and mortality, but also by migration, because people are going in and getting out of that specific country. So it becomes more complicated. Right, but that's the general idea of this formula here. I'm trying to know the population in a specific time point after my base population, and then I use a specific growth rate to project this population to 2030. Let's see that I want to do a different thing. I want to know, I know the population 2000. I know the population 2020 in the world last year. I know that between 2000 and 2020, we had 20 years, T equals 20. I have everything in my formula, so I can calculate the growth rate. I can calculate the growth rate between 2000 and 2020 because we already have the population those years. We know that's 20 years between them. And then I can calculate the growth rate. In that case, I calculate the growth rate, see how it was also in previous years, and then I can try to expect how it's going to be up to the next years. So this formula gives us a lot of possibilities. Understand the growth rate between 2 years that already passed, 2000 and 2020. It can be used to project the population to the next years based on what I think the growth rate is going to be. And it can also be used to understand how many years would it take if this growth rate here, how many years would it take for the population to double in size if this growth rate here continues to be the same in the next decades? So what's the idea? I want to project a population. This population here will double in size. I'm trying to project a population in which it will double in size. And I want to know how many years will it take to double in size. This population here that is going to double in size is going to be 2 times K0. So what I'm trying to find is when this population will reach 2 times K0, 2 times the population that I have right now, the population at the current time. So this number here goes here, and then I have exponential of R, the T that will double, and the population at the beginning of the period. And in this case here, I just cancel this term with this term because they are multiplying both sides of the equation. Or in other words, I transfer this one dividing, it cancels with this one. So I have 2 equals exponential of R time. I want to know the time. That's my idea. So my idea is that I have to put time to the left side of the equation by itself to calculate it. But time here has the exponential. So I will just do the inverse mathematical calculation to get time itself. So I just take the log of exponential of RT, I get RT. But when I do this on this side of the equation, I have to do on the left side. So I get log of 2. R is multiplying T, so it goes to the other side dividing. So it's going to be log of 2 divided by R. So I will have pretty much the T double equals log of 2 divided by R. Log of 2 is a constant. It's 0.6931 and so on. A way to approximate it, you should say that the log of 2 equals 0.7. But this one is called the rule of 69.3 because we pretty much get log of 2, 0.6931, and divide by the current population growth rate. And then it's going to give us how many years would it take for the population to double in size if this growth rate remain the same in these next years. If this growth rate is negative, if the population-specific country is declining, what we're going to get here in T would be how many years the population would decrease by half. If the population keep declining at this negative rate that we might have in a specific country, the T is going to tell us how many years it would take for the population to be K0 divided by 2. Okay? Example, a historical example here. This is a population in the world estimated in 8,000 BC, 5 million people, 1 AD, 250 million people, and then on increasing over time. Based on that formula, the first formula from the previous slide, we can calculate this growth rate here. How did I calculate this growth rate here? The 5 million, if I'm talking about 8 BC to 1 AD. The 5 million is K0. The 250 million is the KT. The time is 8,001 years, right? Here. So I can calculate the growth rate. I have everything else. The same thing for the other years. From 600 to 1,000, the year 1,000. Population at the beginning of the period, 200 million. Put 200 million here. At the end of the period, 250. Put 250 here. How many years you're talking about? 400 years. 400 years. We put it here, then we calculate the growth rate. We have everything else, the population at the beginning, at the end, and 400 years between them, between 600 and the year 1000. So that's how these growth rates were calculated. And between the year 1 and the year 600, the population actually declined from 250 million to 200 million. So that's why the population growth rate here is negative. And now we calculated, we first had the population, and then we calculated the growth rate. And now we pretty much use this final formula here, 0.6931 divided by the growth rate. And then we get these numbers. What do they mean? The population was increasing between 8000 BC until year 1. But it was not increasing so fast. The growth rate was only 0.0005. If the growth rate kept staying that same level, how many years would it take for the population to be 10 million in the world? It would take 1,417 years. That's what this number is saying. What about here? The population was declining, but not so fast, minus 0.0003. What does this result here mean? Since it's negative, what we are saying is like the population of the world will decline from 250 million to 125 million, half of 250, in 1,858 years, if the growth rate continued to be the same one. Did the growth rate continue to be the same one? No. It actually started to be positive. Improvements in the overall mortality of the society, people living more, and also higher fertility. We were still at that time, the pre-transitional society. The society increases, right? And then the same thing goes on. Why is this last column interesting? Why is it important? Because look, in 1815, the population was around 1 billion people in the world. How many years would it take for the population to be 2 billion? 100 years. And then in 1975, the population was around 4.1 billion. How long time would it take for the population to increase to 8.2 billion? Only 43 years. So here, it would increase from 1 to 2 billion. 1 additional billion would take 100 years. Here, from 4 to 8, 4 additional billions, only in 43 years. And why is that? Exactly because the growth rates here are much higher than the growth rates here. Because here, you start to have industrial revolution, improvements in mortality, and so on, and still people having a lot of children. There's a second stage. So the growth rate starts to increase a lot. And then afterwards, the fertility also starts to decline, and the growth rates will start to decline as well. So already started to decline here from 0.018 to 0.015, right? So really basic information, just having the population size in the world for these years, using the first formula here, because we have population at the beginning, at the end, and the time between those years. We calculate the growth rate, and afterwards we use this formula to calculate the doubling time or the halving time. Cool? Here's pretty much the population in the years that it reached exactly 1, 2, 3, 4, 5, 6, and expected to reach 10 billion. And the annual growth rate, it was really high in the 70s because fertility is still really high in the world. and mortality starts to decline fast. And the overall annual increase in medians. How many people increase in the population, births minus deaths, over these years, reaching around 82 million more people per year in 87, 80 in 2011, but then expected to decline exactly because fertility starts to decline. Another way to show the same results, the years in which population reached 3, 4, up to 9 billion. And here also related to the size of the population is the growth rate of the population, the R in that formula that I showed you. It reached the highest level around 1965 and 1970 in the world, and it's expected to decline in these next decades based on several projections, but including the United Nations projections. Whenever we have these projections, we have different scenarios. Here, the medium projection is which you kind of like know that fertility is declining, but in a more stable level. The low projection is the one that you say fertility will decline even more. And the high projection, you say, oh no, fertility might increase a little bit. But overall, by 2100, you also reaching around 11 billion people based on the medium projection, right? And usually when we get these different scenarios from projections, we usually use the medium projection. Same thing here, the medium projection, the high in which fertility could increase a little bit or low, and the fertility actually being constant from previous years that will generate an even much higher society. So these are scenarios that are not realistic. It's just for the idea that we can see if fertility just kept at the same level, the overall size of the population would increase a lot. But we know that fertility will decline. And then we have some other scenarios taking into account different levels of decline of fertility, right? This graph here, just wanted to emphasize, not the graph, this table. These two tables here, population size in billions by continent and by age group, I constructed them, I just originated them by watching this video here by Hans Rosling. I might have told about him before. He was a public health researcher, created this institute Gapminder, and they generate a series of software graphs and videos in this case that shows this statistical and demographic data in a really simple and friendly way. And if you can watch this video here, it's almost 1 hour long, and it's really good. And it's under our course website under days 1 and 2. And he, in this video, he tries to break some of our preconceptions that we think that population is going to keep growing so much and everything, and we don't have a future with the population growing so much. And he just tries to calm us down and show what the projections are estimating for the next decades. So based on a specific part of this video that he talks about population size for the next years, I just organized these two tables here. Let me just show you them. This first one is just the population based on data that he had at that time, 2013, and then projection to 2050 and 2100. The population in the American continent going North, Central, and South America, 1 billion in 2013. The same thing in Europe, Africa, and Asia, 4 billion. So 7 billion people in total. And what's going to happen, what the projections are showing, is that the population is kind of stable in the American continent and the European continent. So it's going to stay around 1 in 2050 and 2100. In Africa, it's going to double from 1 to 2 to 2050. And then it's going to double again to 4 billion by 2100. In Asia, it's going to increase 1 billion by 2050, and then stabilize around that. So the population is now a little more than 7 billion now in 2021, increase up to 9 based on projections, and then 11 billion, then it's going to continue there. So what's we're going to see in these future years is not that much of an increase in the size of the population, but the distribution of the population is going to be much more concentrated in Africa than what it is now. Asia is already a really large continent in terms of population size. And then he breaks it down. I'm sorry, I'm 4:30 now, but let's just finish this. He breaks it down by age group. People between 0 to 14, around 2 billion, 15 to 29, 2 billion, and then the other groups, 1 billion. So these people were just getting older, mortality is declining, so these people get older and get into older groups. So what's pretty much doing now? Fertility is declining, okay, some countries below the replacement level, but on average, roughly around 2 children per woman. So what's going to be pretty much is just these people getting older, and then they are producing these babies here. These people producing these babies, right? This one's producing this one producing that. And since mortality is declining, you're going to have around 1 billion of people with at least 75 years of age and get into these numbers. But overall, the age structure is going to stabilize on that, around the same number of people in these age groups by 2100. Okay? So the quiz today is about the full chapter, world population. We reach until slide 27, but just take a look on slides 28, 9, 30, 31, 32, and 33. It's really based on what we just talked right now. And only until 33. All the material after that is extra. And then on Tuesday, we go into population change in the US. And on Thursday, we have our first exam. Okay? All clear? And if you can, just take a look in that video by Hans Rosling. It's really informative. Thank you very much. Have a great weekend, and I see you guys on Tuesday.